at least I think I finished the proof of the local Tate duality, but I think toward the end there was a little bit sketchy. So let me just sort of quickly review what that argument was. Okay, so roughly speaking, we're in the situation that we have morphisms sort of downward. So we have this sort of long diagram from last time that we always have these sort of h I gk of m going to h2 minus I gk of sort of the punctuality dual twice by 1 and then dual. We always have sort of vertical morphisms, homomorphisms. And we want to show the vertical homomorphisms are all isomorphisms. So what we do know is that if the Galois action on M is trivial, by an explicit calculation that we show that these are all isomorphisms. So therefore, whenever we have these sort of induced modules, these are all isomorphisms. Now we want to show in general case that these vertical maps are all isomorphisms. So last time I said a little bit, I guess a little too fast. Let me sort of give the argument with more details. So let's separate things into several steps. So first I want to show that, I guess the argument goes as follows. We first show that for H0, the corresponding map is surjective. Let me just say for all KE GK, I mean continuous modules. Let me just write modules, sorry, M. Okay, so this basically, if you just look at the diagram here, this is right here. This is automatically surjective because this is isomorphism, roughly speaking. I'm sorry, injective, because this composition is injective, and therefore forcing this first map here to be injective. Sorry, my bad. Injective. And step 2 is that once we prove this for all M, now I want to prove this for degree 1 for all M. For all M. So how do I do that? Well, so now by step 1, we already proved. I guess maybe I should say now we form this long exact sequence. Let me call it star here. Form this star, and by step 1, applied to Q. So I want to apply step 1 not to this M anymore. I want to apply step 1 to Q. So the end result will be somehow in step 1, I would have to choose a different. So in step 1, I would actually doing some Q, induce Q, and then you have another Q prime. The argument, if you somehow really trace back the argument to step 1, that was what's happening. But anyhow, now we already proved the step 1, so this is injective, so therefore this is also injective by our sort of previous step. Now, by 5 lemma, I'm going to skip this part. It's just direct diagram tracing that you show the injectivity for H1, namely this bit here. You can show by 5 lemma. So one of the statements for 5 lemma is that as long as you have this injective, probably this also injective. I don't quite remember somehow. This is isomorphic, so this is enough to imply this is injective. Oh, this first surjective. Oh yeah, okay, good. It's good to have someone in the audience know what's going on. Right. So you have this one. Now step 3 is that now I want to show that H2 of GK M goes to H0 of GK. What is it? M dual 1 dual is also injective. Again, for all M. We follow the same argument. Now I want to apply, every time I apply the previous step to Q. And then I get this being injective. remember the next one is also isomorphism, so therefore I sort of get this this part to be injective as well. And same argument. But just a reminder that somehow when you apply to the previous step, we're working with a different sort of diagram. But somehow it takes forever for me to draw a diagram like so. So we're just going to use the same diagram, but not sort of we're not using the same, literally the same diagram, because over here when I apply to the previous step, the m in the previous step is q here. Okay. And now, so you can repeat this. In particular, you, when you get to sort of to the end of this, we're getting to some sort of GK of Q. Anyways, and supposedly goes down to H3 of GK of M. So this is my step 4. Well, I'm done with H2. So now I look at what happens for H3, which I GK of M. Right, so this was mapping down to H0 of GK of Q dual 1. And this is 0 because the bottom one, remember the way we get the bottom one is start from the, I guess from the 0 to H1, H0, and so writing the long exact sequence to the left, and then dualizing everything. So how you switch in the arrow so that it ends here with 0. There's no H minus 1 here. But then from the previous, by step, by step 3, we know that this is injective. By exactly the same argument as before, even if we don't have a map, somehow you can show this, I don't know, you can show somehow this is injective, and simple diagram chasing shows this is 0. Or maybe if you're not very happy with this, you can somehow make one more step here. GK induced M going down to H0 of GK induced M dual 1 dual. So this is an isomorphism. Because another way to see this is that, I guess, because this is an isomorphism, and so therefore this map to here is surjective, and therefore this is also surjective. This orange part comes from this is being isomorphism, and the white part comes from this is by step 3. So therefore this is also an isomorphism. If these are all isomorphism, then this has to be. I forgot to say. By our earlier calculation, that when you have some sort of trivial when you have some, I mean this is the same as H3 of GL of M, which is 0 because GL acts trivially on M by how we choose our M. And this is 0, and therefore you show that this is also 0. Okay? So that's how you should prove all the vertical maps are injective via these steps. Now, we're going to do this sort of in a dual way, in some sense. Dually, I will use a modified version of this. So I want to go, let's say, 0 goes to R. So I want to use another induction. So there's a slightly different way to induce this. This can be thought of as sort of M tensored with, I guess, Z GL with Z GK. Because of sort of tensor property, so the forbidden reciprocity goes this way, and there's a kernel map R over there. And now you have to now we kind of observe that, but the point that GL has finite index in GK, so this is just the same as induced as representations. And now we kind of work on this side to show that for every M we have this surjectivity, and then go left every time. As it turns out, somehow the 5 lemma this time also works for me. So somehow the injectivity can help you to go from left to right, and the search activity goes from the right to the left for the same argument, by same argument. Show H2 of GKM. Let me just write, maybe write I, subject to H2I of GK of M, dual 1, dual for I equals 2, 1, and 0, and backwards. So start from the right to show search activity. I'm just going to leave that as an exercise for you to check out. But that's sort of a rough idea. So last time, I guess, I wasn't very clear of sort of changing the M. So I was just going to emphasize that we're not just working with one exact sequence. For each of the steps, we have to redo the exact sequence, except I can't write the whole exact sequence. It takes forever for me to write one. So that's somehow the proof of this. Okay. And also maybe I also kind of just add a comment here that in this step here, so we prove the H3 being 0. Then I can use a dimension shifting to show, just like here somehow, if you extend it a little bit, so next one is H3 of Q and H4 of M. If you want to show H4 of M is 0, so you reduce to H3 of Q, which is already known, and use this to show all the H bigger than 2 of GKM being 0. So that's sort of the proof of the local tate duality. Okay. Good. All right. So now I want to talk about the Euler characteristic. For this one, I do have to refer to a couple of black boxes. Which says the following. Just kind of remind you that it says the following. So if you have chi GKM, so set up as before. So K is a local field and M is a finite length OE. So M is a finite length OE module with continuous GK action. Okay. Then we define the Euler characteristic to be alternating sum of the sort of the length of the cohomology. And so the Euler characteristic formula says that if the coefficient has different characteristics, is different from the residual characteristic of K, then the Euler characteristic is 0. Whereas if L equals to P, by our assumption that in this case we always want K to be finite over QP, then this is equal to a minus of the degree of K over QP times the length of M as a OE module. Okay? So that's what we're going to prove now. Okay? So let me first make a remark here. Is that so we have basically we need to show two quantities, right? So this is so Euler characteristic of Galois cohomology of M. On this side is the it's sort of the length of this M. I want to say that the both sides of this equality is so-called additive in M for exact sequences like, whenever you have an exact sequence, as so, then the Euler characteristic of M1 and the Euler characteristic of M2 add up to the Euler characteristic of M, and same for the length, right? So in other words, somehow we don't have to, I guess, prove this for all M, but rather, in some sense, we just need to prove, in some sense, a kind of a basis of, in some sense, a basis of such modules, where that sort of generates the whole category of sort of such modules in some sense. So that's some sort of the point of view we're going to take to prove this. So I guess the first thing we can always do is can reduce to the case when M is a KE vector space, right? As before, I can mod power uniformizer, to filter this thing into things, and also I can even forget about somehow the KE action and basically reduce to FL vector spaces. In the sense that the both sides are some sort of numerical equality. I don't have to look at sort of the K, for example, if M is KE vector space, so this length is just KE dimension over KE, where K is a finite, so this KE is finite over FL, right? I don't have to count dimension over KE. I can count dimension over FL. Sure, no problem, right? And the same here. This doesn't sort of this length is also sort of finite dimensional, so therefore doesn't matter. So I can just basically think of FL vector space. I don't have to think too much about the coefficient. There's no use there. Now I want to introduce a sort of black box somehow. I'll give you a little bit of indication of how this is done, but anyways, so let's say, let G be a finite group. I want to write R. Let's see, what do I want? Maybe for a field K. I will later on consider FL and QL, two cases. Okay? I want to write RK of G for the so-called Grothendieck group of categories of finite dimensional representations of KG. Okay? So what I mean by this is that, let me do this in an extremely explicit way. So basically this is sort of, in some sense, universal way of treating the problem of what I said in the remark, that whenever you have an exact sequence, then I have some sort of a number that's sort of very additive on exact sequences. So then one just might as well just define sort of the category of things that sort of think of whenever you have an exact sequence like this, M is being the same as sort of M1 plus M2 in some sense. So let's make it more explicit. Let's just say that RK of G is defined to be all the B being whenever you have such thing, you can reduce to the case where it's an irreducible representation. So maybe I can just sort of, so therefore this group, in an explicit way, is a direct sum of, it's a free Z module, or free abelian group generated by irreducible representations of KG. And any representation can be, decomposed into sort of finite, into some ways of decomposition of these finite irreducible representations. So this will be, so for example, if you have a W as a representation of Kg, I can associate a class of this is just a sum over all the irreducible representations, and I look at sort of all the multiplicities of this V in this W in some sense, times V. And therefore, every representation of G can be thought of as an element. There's a way to associate class in this group of Grothendieck group. And if I want to evaluate such either the Euler characteristic or this number on the right to this W, I can apply that Euler characteristic or the length to this thing, and then weight it with corresponding multiplicity. But there's also a kind of a more fancy way to write this, which is that you take the direct sum of all the representations, all the finite dimensional representations of Kg, and each one of them you have a ZV, but then you quotient out the relation that V being V prime, direct sum of V double prime, if you have an exact sequence and so on. So basically, if you have an arbitrary representation, you can, I guess, if you have a double like so, you can break it apart into sort of small pieces given by the irreducible ones. So therefore, your W will be equal to, plus sum of smaller ones. That's basically what I write here. Okay? So that's a Grothendieck group of finite dimensional representations of Kg. And then for each subgroup H of G, so we have the induced representation. So given a representation of H, I can induce it to a representation of G. And this also passes to the Grothendieck group. Namely, whenever you have the exact sequence of the H modules, of course, you can induce that. You get an exact sequence of the corresponding induced representation. So therefore, this side being 0 corresponds to the other side, tells you the other side being 0. Okay? And now, here's a theorem. Maybe just add one word before that. Is that so? We basically need to show that this chi gk blah, and I guess the right-hand side of this Euler characteristic. Let me just sort of put a star there. Okay. What I need to show is that these two are the same. I guess maybe what's the word for it? Functional. On the Grothendieck group with values in FL of G. Right? I mean, the left-hand side only, whenever you have the exact sequence, the Euler characteristic is additive. So therefore, you basically can identify somehow the M as a sum of B M1, M2. That's basically what Grothendieck group does. And the other side is also dimension. This, of course, is additive. So therefore, both of these can define. I mean, I should say this. Both of these define something from the Grothendieck group to dimension. So this Z, right? It's a homomorphism, right? Functional. It's a terrible name. Maybe this. Excuse me. Same homomorphism that RFLG to Z. How about that? That's better. Okay? Right? Now let's change this just a tiny bit. Okay, so basically we'll define a map from this Gaussian group to Z, and same for here. In fact, I don't have to prove these are homomorphism from this to Z, the same thing, except I can modify it as long as I can tensor Q and show that rationally they are sort of the same thing. Right? In the sense that I don't have to prove directly for each M over here this characteristic is equal to this side. I can prove that somehow if you have an M, I can direct sum with itself, multiple 100 times. That will have the same characteristic as the dimension side, direct sum 100 times. So that's basically what I want to do. So now, I kind of already hinted that somehow over here, we're going to refer to subgroups of G and their inductions. So here's the theorem. Here's the black box theorem. That is, right, okay. That's the following. So if I take the direct sum, so basically the idea is I want to show that sort of this group here is essentially generated by sort of induction from smaller subgroups with nice properties that I can easily control. So in particular, I just need to take all these subgroups, whereas H is actually cyclic. Nice. And also my L, the coefficient L, does not divide the number of elements in here. And I just need to, hold on a second, FL of H. This will surject onto RFL G. Okay. This map goes sort of it's a direct sum of all the induced inductions and so on. Okay. So what I'm saying is that every representation here, in the virtual way, can be every representation in here can be written as somehow sums and minuses, whatever that means, of representation that's induced from a cyclic subgroup, which has order not divisible by L. Okay. So in other words, if you want to now look at sort of, so for example, Euler characteristic of this, right? If you want to test, two functionals on this one, it's enough to test the two functionals on things over here. But these are relatively easier in the sense that the H is cyclic at least, and there's another nice property here, which will be handy later on. Okay, so that's the essential reduction process. So let me give an indication of how this is proved, but without really going into the details of this. So here's a sketch of this proof. So the argument goes as follows. So we first of all talk about the characteristic zero representations. So we have the same property. Basically, first show that for the characteristic zero representation version, this is okay. For representation L of H. Sorry, there's no direct sum on this side. This is RQL of G plus as so. Okay. So this is so-called Artin's theorem. Essentially, Artin's theorem. Oh wait, I'm sorry. Doesn't have this part yet. Okay, there's no L. Sorry, QL. Like that. So it doesn't have the L part yet. Okay. So I'm allowed to take an arbitrary cyclic subgroup. So this is surjective. The reason is, I guess, just for those who understand what's going on, I guess. The reason is basically this. For whenever you have a finite group, this is the same as the essentially QL G so this is all this Grothendieck group is the same as the character. What's it called? What's it called? Character space of all the characters on G. So namely all the functions that are conjugating invariant under G. So that's a space of all the representation ring or something. Okay, and so I have the induction, but somehow this is dual. This map is dual to the restriction. The surjectivity of the map will correspond to injectivity of the corresponding map. But this is relatively clear because restriction is basically restricting the character of a representation to a subgroup. I mean, every element in G in its conjugated class, every element in G will generate a cyclic subgroup of G. So if a f of G, if a function here is 0, here in the sense that is 0 here, then each f of G is 0 because each G, the group generated by G is a cyclic. So it is one of these things you have already here. So a character on G, if it's 0 on all the cyclic subgroups, then it must be 0 all everywhere. So it's injective down. So when you dualize this, you get the surjectivity. And next, the next step. So this is step 1. The next step is that whenever you have maybe we start from the right-hand side. It doesn't really matter. Whenever you have a representation of G with coefficient in QL, you can. G is a finite group. You can always find a lattice, a ZL lattice of this representation, and then consider sort of mod L representations, just like we discussed earlier. So you start with a V here. You can map it to the reduction. So you take a lattice of this V, and then talk about the reduction of this, and take you don't have to take you take semi-simplification. You get to FL coefficient representation of G. Right, for every QL coefficient representation, you can take a lattice, and the mod L, you get a FL coefficient representation G. And this does not depend on toroidal lattices if you are thinking in terms of Grothendieck groups, because the semi-simplification does not depend. Turns out that this map is surjective. Okay, so this is a theorem. So this is the theorem here. And similarly, we can do the same thing on this side as well. As I said, I'm not going to get the full proof of this. This is sort of just I want it to be a black box here, so I don't want to talk too much about the proof because this is not quite. I guess this is too much different from the purpose of this course, so. And also I don't quite know it very well. So of course, the diagram you can take a representation of H reduction and then induce, and then same thing. So this diagram commutes. By the commutativeness of the diagram, of course, you see that this is surjective. Except that we don't have we'll have another condition that I want my L to be not dividing the order of H. So this part. So I have to add this L does not divide So basically, I want to show that those 60 subgroups where L divides the order has no further contribution to this map. So this is the following. So this is the following observation. So this is about the contribution of characters. Let me just sort of say this in a characters of L group. Let me just sort of discuss the case of L group. In the general case, sort of similar. If I have a second group of order that's sort of I guess L power order, then it has trivial contribution to the right-hand side. That's because the only FL coefficient representation of such H is the trivial representation. Because the coefficient is FL and the group is L group, we know that all FL coefficient representation, only F coefficient, irreducible representation, is a trivial one. Okay? So basically we just have to show the trivial one has no contribution. But then, let's look at somehow what's the contribution of the trivial one. If you have a sort of trivial representation of H, and see what the contribution over the right-hand side is. I want to say that this is the same, essentially gives the same contribution of inducing the regular representation. Because for this H is L group, the regular representation of this is a successive extension of this trivial representation. So in the Gaussian group, it's just basically the number of elements, just some copies of this trivial representation in the Gaussian group. It's not a trivial extension, but somehow, because Gaussian group kills all the extensions, so this is essentially the same thing up to a rational factor. If I'm tested with Q, that's okay. But then this is just the same as essentially inducing from the group 1. Because I guess if you're inducing regular representation, you get the regular representation of G. Well, just maybe, yeah, okay. And that's, okay, this is not trivial, but somehow, I can always take H to be trivial. So this will have the same contribution as the case where H being trivial. So that's already been covered. So I don't have to consider this case. Okay. So that's the reduction that we're going to be using. I know this is used a lot of sort of group theory. I mean, I guess this is sort of very custom in the sense that in the number theory, we sometimes use a lot of sort of facts from finite representation theory of finite groups without giving the proof. We just basically take for granted that this is surjective. Okay, good. So let me maybe keep this for now. So now basically I have to look at sort of representations that are induced from this. Essentially. So now I treat the original Euler characteristic formula. So now I give myself given an FL G K module M. So this will I guess give rise to a representation GK on maybe give a homomorphism from GK to here, which will definitely factor through the Galois group of L over K. Okay, so the action will factor through some finite extension. Now let's see. Just without loss of generality, I'm not sure if I want to use it, but need to use it. But anyways, let's assume that my L is taken a little bit larger so that it contains L's roots of unity. Now I have my L terrible name. F here, K here. So this is my GL over. I haven't used. So let me write this to be my G. Okay. So this is the finite group G, and I'm going to use this black box theorem. So I'll end up getting some H, which is where this group from F to L is Galois, and the Galois group is cyclic. Okay. So by the theorem, I think of this M as a G module. So I can reduce to prove the Euler characteristic formula for M being induced from this H, G, for a subgroup H of G, which is cyclic of order prime to L. Okay. So now this comes down. This does come down to a explicit calculation. So basically, Euler characteristic, you don't get things for free. You just have to do some, I guess, hard work. So once we have this, now we look at each of the cohomology. So Hi of GK of M is now sort of, my GK is, I know it's induced from H to G, but that's the same of inducing from GF to GK, because they have the same cosine segment of M. So therefore, this is the same as looking at, inducing N. Looking at this representation. So looking at this cohomology. But somehow the benefit here is that the action on N factors through this H. It's a cyclic group action. Right. Now, okay, this is okay. So basically, originally I'm looking at the Galois cohomology for K, and because my module is induced from this, I guess some H module here, so I can reduce to calculating Galois cohomology on F. Okay. Oh, very quiet. Now, I have to reduce a little, just a tiny bit further. So I want to look at sort of Galois group of L. I really want to reduce the trivial action, but this doesn't quite act trivially here. But this action of GF on N factors through, I guess, H, which is a cyclic group of order prime to L. So that gives a way to, I guess, kind of to factor further. So remember that maybe this is my GK. This is my K, I guess, K sub, right? So this is GL, and this is GF, right? So GL is a subgroup of GF with quotient H. Now, if I want to compute this cohomology, I can compute it in two ways. It's like taking invariant under GF. I can first take invariant under GL and then take invariant under H. So we have a spectral sequence. Converging to Hi plus J of GL of N. Okay? That looks very scary, but not that much, in the sense that this, okay, whatever that computes, this is the FL vector space. But on the other hand, this group has order prime to L. We talked about a cohomological theory that whenever the group has order prime to L, the coefficient is L torsion. Then all the higher cohomology vanishes. So that all the higher cohomology of this thing vanishes. Okay? So when you really write down this spectral sequence, I don't know how to write this, so this is sort of, okay, H0 of H0. Let me just write this. H0 of H1 is H1 of H0, and so on and so forth, right? All of these terms are all 0 because the outer cohomology, as long as degree is bigger than 0, they all vanishes. So there's no, you don't have to compute any sort of D2 map or whatever. It's still all 0 here. So therefore, all you get, it's just that somehow H0 of H of Hi of GLN is equal to Hi of, oh, excuse me. I'm very sorry. This is F. Sorry. In other words, this is just the left-hand side. Maybe it's better to say this is Hi of GLN invariant under H. So this is this. So far, everything is sort of, I should say, tautology, in the sense that, so whenever you have I guess a quotient, so if the action on this n factors through a group which is relatively prime to L, you can sort of always take that part out and then talk about the inner cohomology directly. So let me write this over here, in case we'll have to do things later. So now, truly, this GLX trivially. So now GLX trivially on N. As I said, I mean, like the whole action only factors through GL. So we're really looking at sort of trivial coefficient Galois cohomology, making our life extremely easier. So this is nothing but Hi of GL of trivial coefficients, FL. Somehow the coefficient, I can take it out. But of course, it doesn't have a trivial action of H, so I have to take H invariant with this N inside. So we just have to compute this. Right? Sorry. Don't copy it just yet. I want to do a small twist to make my life a little bit easier. I want to do the one with the multiplicative group version. But of course, my L, okay, my L is equal to mu L. So all the roots of unity are in L already. So the action is still trivial. So FL is the same as mu L, but somehow the H action on this mu L may not be trivial. So I have to, even if I change inside to be mu L, outside I have to twist by -1 to remember the H action may not be trivial on the cyclotomic character. It's a small subtlety here. Just I feel like this is, it's easier to compute this than FL, but not too much easier. But let's erase this. So now we say the benefit of the black box theorem is that we reduce our theorem to from a general representation M to a kind of a very special case where essentially I have to compute the cohomology for the trivial coefficient or mu L. Really? Okay. So now okay, we reduced I guess the question of computing all the characteristic formulas to Well, essentially just compute the case for mu L. So let's just do that. GL, good. So what would that get? Well, let me sort of write this here. So now I still have this extension, which is cyclic group of order H. I'll use that in a bit. So now I'll get to things that I understand very well. This is just mu L, right? H2, I also know. This is class field theory by local class field theory. And this is with trivial H action. And over here, this is a cyclohamic, I guess, H action. And what is H1? Do I have to do this? Oh, H1. For H1, we use this For H1, we use goes to mu L, goes to L sub cross this is x to the Lth power. Right, the Kummer exact sequence. So maybe next time I don't write this anymore. So right, when we take Galois cohomology, this is L cross. This is racing to the Lth power, and it comes around to H1 here, and by Hilbert 90, this is 0, 1. Usually use 1. It's sort of convention. No choice. So therefore, I get it that H1 of GL of mu L is always canonically isomorphic to this to the Lth power. Right. What do I want? Maybe I want to further decompose this a little bit more. So there's, there's an integral part, there's a valuation part, right? How do I do this? So I have, let's see, I have 1 goes to OL cross, goes to, this is our local field, so to the valuation, right? Now I can, I guess, tensor with Z mod L. Okay, FL maybe. If I'm lazy, right? So I have this obvious valuation thing, and then tensor with FL. So remember that my middle part is what I want here. Okay. So now I want to do the computation, I guess. What exactly do I want? So let me make a so let's make an assumption. A assumption probably will not be true, but anyhow. So let's pretend. Okay. Let's pretend I want to know. I guess I need to know the structure of this OL cross to be able to talk about some things. So let's pretend that OL cross. We know that the group as a group, the structure has a part which is a root of unity. This part about root of unity of L there. That's fine. And let me maybe put an approximation mark. Okay. So the other part we know for ZP, I can take sort of 1 plus ZP, take exponential map, I get ZP. Okay. But for OL in general, you don't. So this is not quite literally isomorphic. But let me, for the moment, let's pretend these are isomorphic to do my calculation. Okay. Let me also pretend a little bit more that we know that L, because L over F over there. So we know that when we prove Hilbert 90, so L as a representation of H is a regular representation of H over F. I want to, let's just for the moment that pretend this is also true integrally. And we will see that this will not matter later. Okay? So let's pretend this to make my life a little bit easier. So then, now if I mod L, so I have two parts, which is somehow coming from this part and this part here, right? And let's see. Let's do this first part first. So this is isomorphic to mu L as an H module. This is because somehow you have mu L, mu L goes to mu L, raising to L's power. You're looking at the co-kernel of this. And there's a kernel of this, right? And we know that, I guess in the, I don't like to say in the Grothendieck group, it's because it's more complicated, but anyways. In the Grothendieck group, these are the same thing. And therefore, in the Grothendieck group, this and this are the same thing. And I guess this is irreducible, so that's okay. So as H module, they are isomorphic. Okay? On the other side, this part here will depend on, I guess, whether L is equal to P or not. Remember, my F is p-adic. F is p-adic, right? So if L is different from P, I mean, this is some very p-adic stuff. So of course, the quotient by L is trivial. But if L equals to P, this just write OF mod P. Okay, that's pretty much what I need, I guess. Except that I kind of have to organize my board a little bit better. Okay. So now let's look at the Euler characteristic. Originally it was GKM, but now it was computing that bit here over here. Look at the dimension of this thing. Let's see. Let me just sort of skip. Oh, okay. Let me just maybe write it like this. Dimension of HI of GL of mu L. Tensor with n twist by -1 together H invariant. Right? So that's just basically. This Euler characteristic is why that's isomorphism. I just have to compute dimension of this guy. And let's see. So I have all the cohomology list up here. It's kind of nice. So now for H0, what's H0? So H0 is mu L. So I have mu L tensor with n minus 1 H. That's sort of the positive part. It says I equals 1. Let's see. Maybe if you allow me, let me try H2 first, because H2 and H1 are easier to write. So H2 is just FL tensor with n minus 1 H. Okay. Now I have to minus H once. Minus the dimension of the following things. Once again, because I guess maybe I should also say that H has order relatively prime to L. And these coefficients are all sort of FL coefficients. So taking H invariant is exact, because there's no hierarchical homology. So although I have exact sequence, it's a sort of genuine exact sequence as so, but when I compute the dimension, I can compute each individual ones, so independently. So there's no problem with this taking H invariant. So now I have to compute basically. Let me write this first, and then I'll erase it. Okay. So I need to consider this tensor with n H, right? But this thing is an extension of these two, and this is by my sort of whatever I pretend it to be is this. Okay. So let me sort of rewrite. As I said, I'm going to erase this. So let's write last term there. So I have my Where's my color chalk? Bad thing, I only bring one back. This is number 1, and there's information number 2, and there's this information number 3. Okay? So let's start with in this order. So number 1 part, so FL tensor minus 1 H. This is all minuses, so this is number 1 part. And then minus the number 2 contribution. So that's the dimension of mu L tensor with n minus 1 H. So this is number 2 contribution. And the dimension of, I guess, this number 3 contribution will depend. If L not equal to P, there's no contribution because that part is 0. If L equals to P, you do have some contribution, which is whatever that is. OF mod P of regular representation. If L equals to P. Oh, the dimension, excuse me. Okay, good. So I have this sort of 3 parts contribution. And you already see that somehow this will cancel with this. And nice. Wait, sorry. This cancels with this. Anyway, they all cancel. Yeah, it's clear. And when L equals not equal to P, this is 0. So great, we're done. When L equals P, maybe here's I mean, there are many ways to say this, but I want to somehow mention I guess somehow a useful statement that you might find later. You might something that's useful you might find later, I guess. That somehow is that whenever you have the regular representation, so if V is a kg module, okay, and if you tensor this V with the regular representation as sort of G acting diagonally, this is always isomorphic as G module or Kg module, doesn't matter. Just copies of Kg to the direct sum of dimension. I don't know a proof off the top of my head, but somehow this is a very useful statement. Basically, regular representation eats off all the representations you have. You just get the regular representation. Direct sum that many dimension times. It's an exercise. You can compute the characters on both sides or something. Oh, of course, there are other ways to prove this. There's tautological ways to prove this, I guess. Anyways, so we have this. So now we know that via that one, this is basically OF, basically tensor n together with no action on H as vector space. Or maybe it's sort of maybe just direct sum dimensions of n times of this one, taking H invariant. And what that dimension is, taking regular representation and H invariant somehow cancels out each other. So in this case, this is equal to the dimension of, or maybe not dimension. It's a dimension. It's a FP vector space dimension. It is a FP vector space. Times the dimension of n. And this is the degree of f over qp times dimension of n. You can go back and check that when m is induced from my h to g, and this is just precisely k over qp of dimension of m earlier. I'm just going to sort of skip this last bit of computation. That's standard computation. And other terms are cancel out. So basically, somehow you see that from, this calculation, this part really comes from, I guess, this units here, where when you exponential it, it somehow becomes a ring of integers. Somehow, basically, the rank of this OL as a ZP module. That's what the sort of the discrepancy there is. And the final remark about this pretendness. Why can we do this? Of course, we can't do that. Of course, we cannot literally do that. But I want to say that, but this is okay. Because indeed, we know that when I invert P, this is true. Okay? Now, somehow what's happening here is that I'm taking, somehow, under this isomorphism, we're taking, my computation uses the lattice OFH inside this sort of, I guess, QP vector space in some sense. And somehow originally asked me to, I guess, use not quite OL, but some sort of lattice that more come from this OL cross. Maybe I should write this cross torsion. So these are two different lattices. But when I do this, computation, I'm doing this modulo some L, where L is, well, I guess it's only matters by L equals P. So I'm quotient all these out by P, and all my computation is sort of is additive and depend only on the Grothendieck group. It doesn't depend on the sort of extensions of these things. So therefore, it does not matter. I can choose any lattice I like to do my computation. In particular, using this lattice is a little bit easier than the other lattice. So that's it. Okay. Choosing two different. So basically, I'm choosing two different lattices and do the mod P, right? So these are not the same module as H modules, but in the Grothendieck group, they're the same. So it will give me the same result. I can use this instead of that to compute because this is easier to compute. So that's it. Okay. Good. Now, let's move on to the global one. I'm roughly behind one lecture, so let's be it. So as before, E is my coefficient field. I'm not going to write that. Oh, maybe before that, I need to just very briefly talk about local duality at a real place. This will only matter if L equals 2. But in our later application, L will not be 2, so somehow we don't need it. Anyway, but still, I'm not giving a lecture, I have to say it. If this is, again, finite length OE module with a Galois group action, then two things. First of all, HI of GR of M, because this group has order 2, and there's I think it's called, what's it called, Tate cyclicity? Thanks. So whenever the degree shifts by 2, they're isomorphic. So I will write H odd and H even instead. H0 is a little bit different somehow. I guess H0 is just invariant of M under the Galois group. But H1 and H1 and bigger ones, there are always 2 torsions. Okay? And Secondly, for star being odd or even, I'll have the cup product. This coproduct is of course this embeds into the coproduct into the sort of even degree with this sort of the dualizing sheaf. Somehow you can think of it kind of a dualizing sheaf, and this cohomology is equal to half of OE over OE. Because I want a kind of duality, so let's embed into the dualizing things. So this is a perfect pair. So now I move to the global duality for Galois cohomology. So my F is a number field, and S a. So I always take S to be a finite set of places containing all Archimedean places and places dividing my prime L. So this is a global duality for Galois cohomology theorem. So if M is a maybe this is maybe a tiny bit weaker than the usual statement you'll see, but somehow I think it's pretty much the only case you use anyways. If you have a finite length OE module with continuous GFS action, and I want to set M star to be the Pontryagin dual, say 0, all HI, all these cohomology are finite. Finite length. Let me mention that about the first statement here, all these cohomology being finite length really depend on your set S is a finite set. Okay. If you allow ramification at infinite many places, this will not be finite. So, well, there is a statement which allowed to talk about sort of allowing infinite many places to be ramified, but in many applications you do when you work on these applications, somehow these finiteness conditions is usually very useful and important. You know, for example, if you don't have this finiteness condition, over here I always say finite length, but when you pass a limit, if you don't have this sort of cohomology being finite, the theory is a little bit weird. So we have a long exact sequence. This is usually called Pato-Tate. Either Pato-Tate long exact sequence or Pato-Tate theorem or whatever. One of them. I need a bigger board for that. maybe I should capitalize long. It's really long. So this is literally a 9-term exact sequence. So here's a recommended way of writing this. I do recommend this. I mean, I know other people have different opinions, but I do recommend this. Because when I give the proof next time, it's how we really see this is how it's written. Oh, how to write this? So let's do a kind of a tricky way, okay? We're going to write something like the long exact sequence associated to some sort of short exact sequence of complexes. So I'm just going to write this. This. Right? You know, later on we're going to do this. I'll have to measure well, but anyways. Since I can erase, so I'm on the blackboard, I can erase, so that's okay. See, you get the rough shape of what's going to happen. But these are not very trivial statements. And so we'll see later. So if you have a global coordinate like so, you can restrict to all these local places at S. So this part is trivial. Sorry. So you have some global coordinate class, you can restrict to the local coordinate class. With a small modification, that over here, so if a place V is Archimedean, namely R or C, I don't use the usual H0, I use the Tate cohomology. Of the scalar group. Or in earlier notation, I just use H even. Then I don't have Tate. I don't need to just use Tate. Okay? So I don't use the H0, usual H0. I use the H0 Tate cohomology of this. And this scalar group is either, I guess, a 2 group or a trivial one. If the trivial one, you don't need there's always 0. So maybe I don't, over here I don't need all the Archimedean ones. So B not equal to C. If B equals to C, all these terms are 0 anyway, so I don't need that. So that's that. But now we'll have to give the last term here. Good. We'll have to give the last term here once I find the 12. Okay. So let me use this bit here as an example of how to get the last term here. So remember that, let's look at here, and I'll tell you what the last term is. So remember that by local Tate duality, this is isomorphic to this dual, right? And if you somehow cover up this star here, you have a global HGFS, but with coefficient M star 1 mapping to that, if you cover this dual here, right? You have a global thing this mapping to here if I don't have this dual here. But now if I dualize it, I have this mapping backwards to that. And that's what I put here. So I put H1 of GFS. Oh, I'm sorry, H0, because when you dualize H2, you get H dual of H0. So this should be the restriction. So this should be the dual of the restriction of H0 to H0. So maybe I should write this as so this is a restriction to V dual. Over here, this is sort of a restriction at V. So this is a direct sum of restriction at V dual, but in degree 0. 0, 1, 2. But it's always Pontryagin dual. When I say dual, I mean Pontryagin dual. So like my coefficient E is finite over EL, QL. So that's something different from this app. Just coefficients. Maybe I should just use QL. Yeah. Okay. So what's non-trivial about this is that why you kind of have a sort of connecting isomorphism, sort of connecting map like this. So this is extremely non-trivial. Okay, we're going to prove this, so maybe not that non-trivial. Okay, what else do I have to say? Oh, this ends here, so niter. Second. So this basically tells you what happens for 0, 1, and 2 degree. And when I greater than or equal to 3, so this HI of GFSM is almost trivial. It's isomorphic to the direct sum of V, all the real places of HI of GFV. Okay. So in particular, if my coefficient QL, the L, if L is greater than or equal to 3, these are all 0. Because we know all the real, for the real Galois group of the real group of the reals, I mean, it's Z mod 2, so if the coefficient has residual characteristics 3, it vanishes. Surprise. Well, let me fit it under here, since I already have some space here. 3. Euler characteristic. So chi of GFSM being I from 0 to 2 of minus 1 I of length of OE of HI. Okay? So one of the things I want to point out is that although this cohomology may be non-trivial when I is greater than or equal to 3, I mean, of course, if the coefficient is not 2, then it's trivial. But even if coefficient is 2, I guess it may not be trivial when degree is greater than or equal to 3. The definition of Euler characteristic only goes up to degree 2. Okay, this is simple. I guess you can think that's a kind of a technical definition, but anyhow, the statement that this is equal to summation of all the places you're removed, the local characteristic. A quick comment is that over there, I use sort of the Tate cohomology at the Archimedean places. But when I do this calculation over here, I use the usual Euler characteristic. And for degree up to I guess for degrees in I equals 0, 1, and 2. Okay, I don't take the third term. Although of course in the real place you do have the third term, but that's going to be isomorphic to what you have over here. I guess somehow you can you could add to any number here, and then you have this side adding to the same number here. They'll be equal. So after the third term, after I guess starting from the third term, the corresponding column will have the same characteristic anyways. Here's a more explicit formula for this. So of course we have a local Euler characteristic formula for the local terms. You can write it out, and this is equal to the degree of f over q of the length plus for all the Archimedean component, you're taking the length of the H0. Or maybe just write m of GFE. So usually when you see in the literature, it's written in this form. But sometimes I found it more suggesting when you read it in this form. Yes. Why are these two equal? Well, you're summing over all the local places, right? At places, so S has several things, right? Either those are places where, I guess, V divide L, or not divide L, or infinity places, right? If your V does not divide L, the corresponding local Euler characteristic is 0, we just proved. But if it divides L, it will get something like minus of the local degree extension times the length. But if you sum over all the places above L, you just have the same of degree of the number field f over q times that. So that's the minus part of this. And the Archimedean place, we note that H0 and H1 and H2 have the same cardinality, and therefore you just left with H0. So that's the equality you have. But I guess usually people write in this form, but not this way. I like this one better. Right. So let me, before erasing the local Tate duality, let me make a remark here that this local Tate duality, this 9-term, excuse me, Plato-Tate long exact sequence 9-term is self-dual. If you look at it, it is sort of self-dual. It's that if you take dual of this whole thing, it will go from 0 to H0 of this, and then because you dualize this, it's going to be H0 of the M dual 1 of this and go backwards. So maybe, I just don't want to erase anything bad. So remark 1 is that Plato-Tate for M, if you somehow take the punctuality dual of the entire 9-term exact sequence, that's the same as the Plato-Tate for M dual 1. Okay? If you dualize the entire spectral sequence, I mean, under the local Tate duality, of course, you have to dualize this to H0 of the dual, and it's H1 of the dual, H2 of the dual. And the remark 2, I can erase this part. Okay. Remark 2 is that another way to think about the Plato-Tate duality is that you can set, basically another way to think of it is somehow you look at it over here. You look at this boundary map as so. This boundary map will tell you that the kernel of this thing is going to be equal to the co-kernel of this thing here, right? This long exact sequence, I guess exactness, here says that the kernel of this map is going to be the co-kernel of this map. But the co-kernel of this map is, because it's dualized, it's going to be the dual of the kernel of this thing here. So if I set for I equals 1 and 2, I can set SHA I of GFS M to be the kernel of hi of GFSM to these local things, V in S of hi GFVM. Then somehow there's a perfect pairing between the SHA-1, namely the kernel of the thing, and the somehow co-kernel of the dual. I mean, like if you dualize it over, you have somehow the perfect pairing of the SHA-1 and SHA-2 of this. Because if you did not, because traditionally it's denoted by SHA, I don't know why it's called SHA. Okay, so that's the two ways of thinking about this. Are there any questions regarding this? So yeah. So the question was that why are these somehow locally? I guess for Archimedean component, why are they the same? That's because over here, when you compute, this is just a dimension of H0 of GFVM. This is precisely this term. Well, I mean, okay, I should write length. And then there's a length of H1 and the length of H2, right? And as it turns out, somehow length of H1 and 2 are the same. Yeah, because this is a Herbrand quotient. Is that okay? Because M is finite, so by Herbrand quotient they have the same size. Okay, good, thank you. So I have about less than 10 minutes. Let me try to say a little bit about the input from global class field theory. And next time I'll give the proof of this. Huh? Okay, so input. Global class field theory. Right? Oh, GCFT. So what do I want from global class field theory? For finite Galois extension, L of F, we have first of all H1 of the L cross over AL cross being trivial, and H2 of this being 1 over L over F Z over Z. Okay? So those are the two things you proved. So this is I don't know what it's called. Something from the class formation. Okay? So now I want to take limit over sub-extensions L inside. So whenever I talk about GSFS, it's a Galois group of the maximal extension of F that's iramified outside S. So I only take this, sort of this thing, this limit over inside that. So I will get H2 of really GFS. I mean, I guess I'll write what 1 does, but let's do 2 first. Of FS cross let me formally write AF as cross. When I write this, I really mean sort of the limit of such things. And somehow, I only care about the L-adic version of this. So let's tensor with ZL. So I will get only the part QL mod ZL. Okay? There's a little bit of a subtlety. I mean, what I really want is I don't do this, I will get Q mod L, Q mod Z. But this requires that this degree can have C arbitrarily large denominators. But if I don't allow ramifications, I don't know how to construct sort of extensions of this F with arbitrarily large degree, when the degree is arbitrarily divisible. So this requires that the degree of such L over F is infinitely divisible, L divisible. Or maybe for any power of L, you can find an extension where the degree is divisible by L to the n, not n. But this is okay here. Okay here, because I can take the cyclotomic one. This is contained in Fs. Because S contains all the places above L. So this thing only ramifies at L. So this belongs here. So this degree can be arbitrarily sort of L divisible. But for other primes other than L, I don't know how to. I guess Mueller said that he doesn't know how to construct such an extension. I guess it's not known. About others, this I really do need some sort of black box. Again, I tensor with ZL. Of course, when I equals 0, this is just whatever the thing is, just whatever, take invariance, just F and AF, tensor with ZL, because I use ZL coefficients. And I want to assume that others are all 0. This requires a little bit of proof. I don't know how to. There's no time for me to present that. I guess for 1, you just take a limit over here. But the vanishing one, I greater than or equal to 3, takes a bit of time. So I'll just take that for granted. So this follows, if you want to know how this is proved, this follows from the this class formation thing, and there's a Tate-Nakayama isomorphism relating this with a constant coefficient. But somehow, as you take the limit, when I greater than or equal to 3, the corresponding map on this side correspond on the other side to multiplication by the degree of the extension. Therefore, in the limit, it becomes trivial. So that's a rough idea of how it was proved. But for now, let's say we're happy with this. I do need a subtle technical point, which is that, of course, on the right-hand side, I'm looking at this cohomology over here. Or maybe sometimes it's useful to quotient out let me finish this one, maybe. You quotient out by the part that's sort of at place not in S. I want to say this is sort of the same as OF cross. I want an integral version of this, basically. It's a little bit technical. Maybe I'll just let me sort of ended with here. I'll pick up next time. So somehow this doesn't quite because I want to look at GFS. I wanted some sort of integral version of this. So this is sort of as integral version of that statement. So I want these to be isomorphic. I'll talk about this next time.